All right, so this is week 12, and we're preparing for exam 3. I believe I've actually already done this example. I did it when it was part of the exam 2 review. Well, I guess we'll try to do the following here. I'm not sure what my results were for this one. Let's just try to do it. Okay. Yeah, so we have this is instrument shown has a mass of 43 kilograms and is spring mounted to a horizontal base. If the amplitude of the vertical vibration is 10 millimeters, or 0.1 millimeters, I should say, right, so that's going to be our Y, right? We call it Y, they're calling it XB, is 0.1 millimeters. And calculate the range of frequencies, Fn, of the base vibration, which must be prohibited if the amplitude of the vertical vibration of the instrument, let's call it X. It actually should be called Z, I think. Yeah, we should call this the Z, because it's internal to the thing, and it's going to measure relative motion, and it's the limit is going to be 0.15 millimeters. And we want to find the range of this. Each of the 4 identical springs has a stiffness of 7.2 kilonewtons, which turns out to make a total of 28,800 newtons per meter, kilonewtons per meter. All right, so I think we got a lot of stuff going on here. We're going to assume that it's undamped. Sure. So I'll assume undamped. And we'll pretend I spelled it right. So I'll get the natural frequency first, because we can. 40, oops, upside down. 28,800 divided by 43. Then we get a natural frequency of 25.88 radians per second. And if we also might want to get the, right, so by the way, I think they confused me by putting an N right there. I think we wanted F, right? So we want to find the range of frequencies, the base vibration, right? So we don't want N. N is the natural frequency, and they either messed up or they're using a different subscript for things, because this is actually the base vibration that's forcing this to happen. So we have 2 pi times, I want natural frequency divided by 2 pi. There you go. So that ends up being 4.119 hertz. That's not a lot. So let's see. We'll write out what this should be. This is, I'm gonna use this as a vibrometer, and we'll see if we're in kind of the range that would make sense, right? So here's the part where I'm about to mess this thing up right here. I think we should be using, right? So I'm not sure I agree with the authors here on what we should use. Is Miriam and Craig, and if we go back to our equations, let me just pause this for a second. All right, I was just looking at my previous solution. The reason why we're going to use a different, excuse me, let me come back to this. The reason why we're going to use a different equation to get this answer right here is because they didn't ask for the relative motion, right? They just asked for the motion of the machine. So it's not really what the machine is measuring, and which seems kind of messed up. So I'm going to do it the way that would get these correct answers, and then I'm going to redo it with what I believe should have been done. Right. So here is, we're just talking about motion. So here's the ratio of these two motions that we're like kind of aiming for, 1.5. Now, based on some things that happened before week 9, we're really just taking a look between the actual motion of this guy right here and the actual motion of those two things. So that's that ratio. So really, in here, I'm going to say that the limit is in x, right? Because remember that, recall why I'm doing this, is that z was equal to x minus y, right? And that's why we started using the z's. But we're back at looking at just at x right here. So as a view of an x, so that means that we have this 1 minus r squared behavior that we want to look at. And we try to find what the r's are going to be required. Oops, get back to that. What r's are required to cause that. So we end up getting 1 minus r squared absolute value is equal to 1 over 1.5, which we know is 0.6667. All right. Now, you have a choice when you of whether to go positive and negative on this. Essentially, if are we subtracting 1 from this and taking the square root, or are we adding 1 to it and taking the square root of it? So the two choices are 0.5774 or 1.291. And then multiplying them by this value right up there, we'll see that we have Fn. And once again, you don't know F, right? Because R is equal to FF over Fn right here. So therefore, FF is going to be R times Fn, or 0.5774 times our 4.119. And that ends up being 2.378 hertz, which we can see is what we got. And then the or equal to 1.291, 4.119. And we end up with 5.318 hertz. So that's obviously what the author wanted us to do. But this is a dynamics book, and they're not really, they didn't go into the detail of what the instrument should be measuring, because the instrument actually internally sees z. Even though the instrument is moving x with respect to y, it's also moving y. So the total amount that it's moving is z. So we should probably instead take our z over y. Right, so now we're using that same criteria there, that it's going to be say criteria, same data, 0.5, maybe that's the internal measurement that gets seen on the little screen thing here. See that little screen right there? So that's what that z is going to measure, as opposed to something and seeing how much this guy moves right there, its actual movement of the thing. It's like a relative movement, right? So that's a 1.5. And now we have equal to r squared over 1 minus r squared, right? So this is the equation, and that too is absolute value, because we end up taking the square root somewhere in there if for no other reason. So now what we do is take r squared is going to be equal to 1.5 times 1 minus r squared. Of course, that's absolute value of that. You have to decide whether it's going to be positive or negative. And you get r is equal to 0.7746 or 1.732. Now, neither one of these are accelerometer ranges, which is about 0.2, right? And unfortunately, both of them are damped. So this is not the greatest setup if you go for the vibrometer type of thing, because we want to be over 3, way larger than 3 if we're using a vibrometer, or less than 0.2 if we're going to use an accelerometer. So this is not going well for the home team. But plugging those things back in to the into the same equation right here with that natural frequency, we get a range of 3.191 to 7.134 hertz. So it's off from here. It's shifted to the right some, but we still have within a reasonable sort of range. But yeah, this is what Miriam and Craig decided to do. So I figured it was an example to use. I don't know if it's the greatest example because they are following this type of logic, whereas we already know that the instrument the thing would be registering would be the Z. I've repeated that enough times. We'll see the next example.